This section introduces the single reinterpretation that generates the whole book. Read one formal language under a second model, and if the reading is faithful, every theorem on each side becomes a theorem on the other. That Rosetta move is the chapter. Martin Leff. Type theory's types are reread as spaces up to homotopy. Its identity type, A equals B, becomes the space of paths from A to B. Equality stops being a bare proposition and becomes a structured object carrying its own higher equalities. This is the single surprise that reorganizes everything. Voevodsky's univalence then legislates the working mathematician's daily habit that isomorphic structures are the same into the foundation itself. The book is the first systematic exposition of what that one reinterpretation generates. Univalent foundations. This section explains how one reinterpretation of equality turns type theory into homotopy theory. Read the equality of two terms, not as a yes or no proposition, but as a space, the space of paths between them, and type theory becomes homotopy theory. That single reinterpretation seeds the whole book. A type is a space. Its terms are points, a proof that A equals B is a path, a proof that A equals B is a path. A proof between two such proofs is a homotopy, an infinity, groupoid. From it, the two novelties fall out. The first is Voevodsky's univalence, where isomorphic structures are genuinely equal. The second is higher inductive types, which construct spheres and truncations as pure logic. Set theory cannot see any of this. There, equality is a bare proposition with no interior, so identifying isomorphic things stays a workday convenience that the official foundation forbids. This section explains type theory as a self-sufficient foundation built on a single primitive. Set theory runs on two floors. First-order logic sits underneath, and the ZFC axioms are built inside it. So set theory is forever about the interplay of propositions and sets. Type theory demolishes the staircase. It is one self-sufficient deductive system with one primitive, the type. Proving a theorem and constructing an object become the same act, because a proposition simply is a type, and its proof is an inhabitant of that type. The whole chapter turns on a single judgment, written A, which reads, A is a term of type. A, it looks like the membership statement. A is an element of A, but it is categorically unlike it. A judgment lives in the meta-theory. It is external, and it cannot be negated or disproved the way the internal proposition that A is an element of A is an element of A is an element of A can. This section explains how type theory folds two things into one. Set theory runs on two stacked layers. First-order logic sits underneath. The ZFC axioms are built inside it, and sets and propositions stand as separate kinds of thing. Type theory's founding move collapses both into one self-standing deductive system with a single primitive, the type. Everything the chapter unfolds is downstream of that collapse. A proposition is a type. Proving it is constructing an inhabitant, an element, A of type A. And membership becomes a judgment rather than a proposition. You cannot negate the claim that A has type A, nor name an element apart from its type. Where set theory's membership symbol related to pre-existing objects. Here, the object has no existence prior to its type. One layer, and the logic falls out for free. This section explains the single reinterpretation that carries the whole chapter of homotopy type theory. Read the identity type of A and B in A as the space of paths from A to B. The older reading treats equality as a truth value, a yes or no predicate. Here, equality becomes a structured object instead, paths, then paths between paths, and so on indefinitely upward. Because equality now has this shape, logic inherits the geometry of homeward. Univalence then closes the loop. A path between two spaces in the universe is an equivalence between them, so equivalent structures are literally equal. The generative move is twofold. A proof of equality becomes a path, and identity is identified with equivalence. That single move is what lets one language serve simultaneously as homotopy, as logic, and as a foundation for mathematics. This part explains why every type in homotopy type theory secretly carries an infinite tower of higher structure, and why one rule generates all of it. Equality is a path. A proof that two proofs of equality agree is a path between paths. Iterate that move, and every type silently carries an infinite tower of higher structure, a weak infinity, groupoid. The surprise is that none of this tower is axiomatized. One rule generates all of it. The induction principle for identity types, it says that any construction depending on an arbitrary path P, a proof that x equals y, is fixed once you supply it on the reflexivity path at x alone. Symmetry, transitivity, associativity up to higher path. Everything falls out of the x alone. Space turns synthetic here. Points and paths are primitive, not assembled from coordinates. The boundary is this. For set-like types such as the natural numbers, the tower collapses to nothing. The geometry lights up only where identifications branch. This section explains why classical logic and set theory are a subclass of types. Classical logic and set theory are a subclass of types, carved out by forbidding higher path structure. A type is a set when any two proofs of an equality are themselves equal, with no non-trivial paths between paths. This is definition. 3.1. One rung lower. Libs a proposition, a type with at most one inhabitant. Proof. A one rung inhabitant. So, and, or, for all, there exists become operations on types, but only once you truncate away the surplus structure a naive reading would retain. That surplus is exactly the ambiguity the chapter opens by naming. The single move is this. Logic is the proposition, truncated fragment of the same universe, and sets are the zero truncated one. One knob, homotopy level, tunes how much classical mathematics you recover. This section explains why type theory needs a notion of triviality to recover ordinary logic. Type theory hands you more than one way to read and exists and not. The propositions as types dictionary is too generous. It proves statements, such as the axiom of choice, that classical logic keeps optional. The chapter's move is stratification by triviality. A type is a set when its paths are trivial. It is a proposition when even its points are trivial, any two of them equal. This ladder runs through the -1 types, the 0 types, the 1 types. Each rung sheds one layer of higher homotopy, and the ladder is upward closed. Logic is then not new machinery. It is propositions as types restricted to the -1 truncation, where a type records only whether it is inhabited, never how many ways. Sets, the 0th rung, are where ordinary mathematics comes to live. This section explains why homotopy type theory treats being an equivalence as a mere proposition instead of as extra structure. A map carries. Start from the quasi-inverse. A function's having an inverse is data the function carries, not a bare property. The quasi-inverse of F bundles a chosen inverse, G, together with its two homotopies, x equals x, hex equals x, hex x, hextra D. After F and F after G each return to the identity. That bundle can be inhabited in genuinely different ways. Lemma 4.1.1 shows it has as many inhabitants as the type of self-identifications. The dependent product over x and a of the identity type x equals x has loops. The consequence is uncomfortable. Being an equivalence would then be structure. A map carries something with internal variation rather than a settled fact about it. A single map could count as an equivalence in many distinct ways, and that plurality is what the chapter sets out to remove. The chapter's one move is to repair this. It finds a predicate, the is equivalence predicate on F, squeezed between the quasi-inverse on both sides, yet itself a mere proposition, true in at most one way. Three constructions all achieve this and are mutually equivalent: the half-adjoint equivalence, the bi-invertible map, and the contractible fibers formulation. The primitive underneath is that coherence buys uniqueness. Adding just enough witness data collapses the whole space of witnesses down to a single point. This section explains why being an equivalence should be a property rather than a choice. A function is an equivalence in at most one way. The naive definition is the quasi-inverse of F, written chin V of F. It violates this. Its witness type is equivalent to the product over x in A of the identity type x equals x, which is provably not a mere proposition. So one map can carry many inequivalent inverses. The chapter's move repairs proof relevance by adding coherence. Three definitions do this: the half-adjoint equivalence, bi-invertible maps, and contractible fibers. Each patches the quasi-inverse by supplying just enough extra data, a coherence path, tau, a second inverse or contractibility, to collapse the redundant witnesses to a point. All three are mere propositions, mutually equivalent, and logically identical to the quasi-inverse. The primitive structure becomes property by adding coherence until the witness type contracts. This part explains induction as the single pattern behind inductive types. Almost every way of building a type, the coproduct, the product, the natural numbers, lists, collapses to one pattern, a type freely generated by its constructors. The chapter's move is to stop asking what the elements are, and instead pin the type by how you map out of it. That is the induction principle. To define a function on the whole type, you give a value at each constructor with recursive calls permitted on the constructor arguments. The computation rules force agreement there. Freely generated means no element exists, but those the constructors compel. So this map out data always suffices, and it suffices uniquely. An inductive type is what its induction principle lets you do with it. This is the same Yoneda posture, an object defined by its maps. This part explains how the inductive types of Chapter 1 all reduce to a single schema. Almost every type former from Chapter 1 collapses into one schema. An inductive type is freely generated by its constructors. There is nothing in it but what repeated constructor application builds. The chapter's move is dual, and it is the move that makes the whole account go through. To use such a type, the induction principle says that a dependent map out of it is completely fixed by its values on the constructors, with the inductive hypothesis supplied at the recursive arguments. Generation and elimination are two faces of one universal property. The type is initial among all structures carrying those constructors, This is why the constructors, the eliminator, and the computation rules together pin the type down uniquely, shown in section 5.2 by way of univalence. Hold this primitive. Later, the higher inductive types are the same pattern, with the constructors merely extended to paths. This section explains higher inductive types, the primitive that lets a type be presented by generators and relations at every dimension at once. Start from ordinary induction. It generates a type by declaring its points. The constructors say what inhabits the type, nothing more. A higher inductive type lifts that same move up one dimension. Now the constructors may also emit paths, which are inhabitants of the identity type, and paths between those paths, with no ceiling on how high the tower goes. Take the circle. The circle is one point called base, together with one generating path called loop, where loop is an equality from base to base, freely posited. Point and equality stand on equal footing, both handed to you by constructors. That equal footing is the whole primitive. A higher inductive type is a type presented by generators and relations at every dimension simultaneously, points and equalities together. This is why synthetic homotopy becomes possible. A space is now definable directly by its cells, and the induction principle already knows to carry the path constructors along. This section explains higher inductive types and how they lift free generation into dimension. An inductive type is fixed entirely by its constructors, and its induction principle is its universal property. Higher inductive types make a single move. They let constructors inhabit any dimension, so they generate not only points, but paths and paths between paths. Take the circle S1. It is the point base plus a single constructor loop, a path from base to base. This is structurally the same act as generating the natural numbers from 0 and successor, only now the successor builds a path rather than another point. The primitive, to carry away, is free generation, lifted to infinity groupoids. And because a groupoid carries operations on its paths, the generation overflows its inputs. The path loop, the composite loop after loop, and the inverse loop inverse are all distinct, and none of them was put in by hand. Ordinary induction yields only what you inserted. Here, the dimension, raising operations on paths manufacture the rest. This section explains how a type's complexity is read off its own paths, recursively. A type X is an n-type when every identity type, x equals y, is an n-1 type. The latter bottoms out at -2, where contractible means one point up to homotopy. The predicate defines itself one dimension down. This is the very move that made a set, a type whose paths are mere propositions, now iterated the whole way up. So truncation is a ladder, cumulative in one direction only. An n-type is automatically an n+1 type, never the reverse. The height above which the homotopy goes quiet can only rise. Its mirror is connectedness, trivial homotopy below n rather than above. Connectedness pairs with truncation into a factorization. Every map obeys, the -1 case being ordinary surjection, then injection. This part explains what the complexity of a space means in homotopy type theory, and how a single recursive rule generates the whole hierarchy of levels. A space's complexity is the depth at which its tower of paths between paths goes trivial, and one recursion captures the entire hierarchy. X is an n-type exactly when every identity type, x equals y, is an n-1 type, bottoming out at contractibility at n equals -2. Sets, mere propositions, and contractible types are simply levels 0, -1, and -2, the places where the tower flattens. They are the same notion, read at different depths. The dual reading, NAC connectedness, is triviality up through level n. Truncated and connected are the two halves of one orthogonal factorization system. At n equals -1, that system is precisely surjection, followed by embedding, ordinary image factorization, lifted to every dimension by a single recursive predicate. This section explains why homotopy theory becomes synthetic once you read it through the identity type. A space is its type of points. A path is a proof of identity. A homotopy is a path between paths, and the entire tower is generated for free by the rules of the identity type. That single move makes homotopy theory synthetic. You prove associativity of path concatenation by path induction, never by reparametrizing maps from the unit interval into X, and never by filling horns. Spaces enter directly through the universal properties of the higher inductives, the circle, the sphere, and the hop vibration, each read as a higher inductives, the circle, the sphere, and the hop vibration. The primitive to carry forward is this. The identity type is an infinity groupoid, so the combinatorial models dissolve into type formation rules. The payoff lives at the boundary because no proof names a concrete model, so each one holds automatically in every infinity comma, one topos, not just in spaces. This section explains the synthetic move at the heart of homotopy type theory, the dictionary that turns geometry into type theory. Space becomes type. Point becomes element. Path becomes proof of identity. Once that dictionary holds, all of homotopy theory is already present in the rules for the identity type, whose infinity groupoid structure those rules silently generate. This is the synthetic move. You never present a space, no maps out of the unit interval from 0 to 1, no horn filling. You name it by universal property as a higher inductive type, and you reason by path induction. The payoff, the chapter exists to earn, is abstraction and elementarity at once. Because the proofs cite no model, they hold in every model. Con. Simplicial sets, classical spaces, any infinity. One topos. Here is the surprise it will cash out. The third homotopy group of the two-sphere equals the integers. It falls out of the interchange law from a type with no 3 cells. This part explains why category theory sits more naturally in univalent foundations than in set theory, and what the definition of a category becomes once you make that choice. Category theory refuses set theory because it only ever cares about objects up to isomorphism, yet set equality is stricter than that. That mismatch is a friction the whole subject quietly works around. Univalence already resolved exactly this, one level down, by declaring type equality to be equivalence. A category is that same move, reapplied to objects. You impose that the identity type between X and Y in the object type A0 is equivalent to the type of isomorphisms from X to Y. Drop that axiom and you get a precategory. Force the object type A0 to be a set instead, and you get a strict category. The chapter's telos is to show that the univalent choice is the right one. Under it, the statement fully faithful and essentially surjective implies equivalence turns from a form of choice into a theorem, because saturating equality to isomorphism was the missing content all along. This section explains univalence, reapplied one level up at the level of category theory. The smallest move, univalence, comes back a level higher. Set, theoretic foundations force equality onto structures that only ever respect isomorphism. Category, Theory is the sharpest victim. It is invariant under isomorphism of objects and equivalence of categories, a sameness that set theory cannot see. The fix repeats the univalence pattern. Demand that identity of objects simply be isomorphism, that the map id2 iso be an equivalence, and a mere precategory becomes a category. Every pathology is downstream of the original mismatch. The chapter's tell is this. The claim that every fully faithful, essentially surjective functor is an equivalence, needs the axiom of choice for strict categories, is unprovable for precategories, and becomes a choice-free theorem for categories. Isomorphic objects are equal. The correct definition was hiding in the notion of equivalence all along. This section explains why set theory needs no primitive membership relation once you work with types. A set is a zero type, a type whose equality is already trivial, with nothing higher hiding underneath, as section 3.1 established. The chapter's whole wager is that everything Zermelo and Frankel build from the global membership relation, the one written as is a member of, survives without that relation. The category of zero types, called set, already carries the usual structure, completeness, images, exponentials, a pi-w predopos, and elementary topos under propositional resizing, and Lavery's ETCS, under the law of excluded middle plus the axiom of choice. Cardinals and ordinals, traditionally encoded through membership, turn structural. Univalence makes the structural encoding as convenient as the material one. Even Zermelo and Frankel's cumulative hierarchy reappears, but as a higher inductive type with membership constructed rather than assumed. The move is this: replace substance, what a set contains, with structure, how it maps, and lose nothing. This section explains what a set becomes, once mathematics rests on univalence rather than on membership. A set is a truncation level. It is the zero types, the types whose only homotopy is bare equality. Everything the membership hierarchy classically provides, univalence provides structurally instead. The category set recovers the ordinary one exactly. It is a pi, w, pretopos, a topos under propositional resizing, and a model of Lauver's ETCS under the law of excluded middle plus the axiom of choice. Working mathematicians lose nothing. Cardinals and ordinals, classically built from global membership, become invariants of sets and of well-ordered sets themselves. Zermelo. Frankel's cumulative hierarchy is no longer foundational. It is constructed one higher inductive type with membership and afterthought. Set theory stops being the ground. Everything stands on and becomes one more definable object inside the theory. This section explains why the real numbers have two completeness properties that point in opposite directions. Completeness has a direction. Dedekind's version, closure undercuts, makes the reals the final Archimedean ordered field. Cauchy's version, closure under limits of sequences, makes them the initial Cauchy, complete one. Classically, these describe the same object, but constructively they are two universal properties pointing opposite ways, and a real is whatever satisfies them, not any chosen set of cuts or sequences. The chapter's move is this. A higher inductive type builds the initial object directly, folding completion and quotient into one simultaneous constructor and path definition. So the Cauchy reals need neither the impredicative power sets that Dedekind leans on, nor the countable choice that the classical Cauchy construction leans on. This is a third way, sidestepping the comparable choice that the classical Cauchy construction leans on. This section explains what the real numbers are for and why completeness is a universal property rather than something you check. Stop asking what a real number is and ask what the reals are for. The Dedekind reals are the final Archimedean ordered field, and the Cauchy reals are the initial object, or initial object, objecti. Complete one. Two flavors of completeness, closure under cuts and closure under limits, become two universal properties. Each construction, whether by cuts or by a Cauchy approximation higher inductive, the payload survives constructively. It is the same an object is what. It does move that classical analysis smuggles in, and the higher inductive type Cauchy reals pay for it with neither power sets nor countable choice, the two compromises every older constructive reel demanded. Completeness stops being a property you check and becomes the closure the universal arrow already in check and becomes the closure the universal arrow already encodes. This section explains what it means to turn type theory from the tool into the object of study. Every prior chapter did mathematics inside type theory. This appendix makes type theory itself the thing you examine. The move is the object language and meta-language split, which the author names directly, just as the theory called ZFC, rather than init, deposes a practice of sets that one already trusts informally. A formal version of HOTT is built in two stages. First, the syntax of terms, then the judgments and their inference rules. That formal object is what lets you prove things about the theory rather than init, consistency, models in higher toposes, implementation in Kokonagda. Why bother? The fact that no term inhabits the empty type, the type written 0, is not free. A mistaken definition of equivalence, one that forced 0 to be equivalent to 1, would let univalence populate the empty type. Consistency is a meta-theorem, and a meta-theorem needs a formal object to quantify over. This section explains what the final appendix does and why it stands apart from the rest of the book. Everything the book does happens inside the system. This appendix builds the system as an object you can stand outside of and reason about. That reflective turn is the whole point. Informal univalent mathematics never names its own rules. But you cannot prove homotopy type theory consistent, that is, that no term of type 0 exists. You cannot model it in simplicial sets or higher toposes. You cannot run it in Kok or Agda until the rules become a mathematical object rather than a practice. So the chapter makes the syntax explicit, terms, judgments in context, written as a has type A in context, gamma, and inference rules. The primitive here is the split between the object language and the meta-language. Questions like, is the type 0 empty, are unanswerable from within. They can only be answered from above.